Hello and welcome to Information Technology Video Developer Network. My name is Abdurrashid Hamid. I'm a certified Microsoft specialist working for Cyber Bionic Systematics. The topic of our lesson today is logical and bitwise statements. So before we start our lesson, let's take a moment and understand the meaning of our topic today. The topic, I repeat, is logical and bitwise statements. But what is a statement? A statement is a meaningful declarative sentence or expression that is either true or false. So a statement can be true and a statement can be false. A logical statement is just like a Boolean statement here. You have true and false. For example, if I tell you that the world is round, you know that my sentence or my statement is true. If I say the world is flat, immediately you know that the world is not flat, thereby rendering my statement to be false. So that is a type of statement. For logical statements, we always have true or false. And for bitwise statements, we don't have true or false. Bit, you remember, is the short form of binary. So binary doesn't have true or false. It has ones and zeros. So here we have a bitwise statement can either be 1 or 0. That's the difference between logical and bitwise statements. In logical, we have true or false, and in bitwise, we have 1 or 0. So now that we have made this clear, let's move to the next slide and see an example. Here we have and. Everybody knows and. If I say my pen and your pen, it means both pens, yeah? So here we have these two ampersand signs representing and in this logical conjunction. This is a logical conjunction. Why? Because we have true or false results. So here, what we mean by this conjunction is a logical operation closed by its implementation to conjunction and. Now, this means that we are simply joining two or uniting two statements together and seeing if they are both true or one of them is true or both of them are not true. So here we compare them, we join them, and we have a result. An operand is just like, let's say, a statement that can have value of true or false. So this statement can either be true or false, and this operand can also be true or false, just like an operation sign. Now, right down here you have the truth table. The truth table for the operation of the conjunction of two Boolean expressions. We have the first expression and the second expression. So it's like having operand 1 and operand 2. Operand 1 can either be true or false. Operand 2 can also either be true or false. And then we get a result. Our result can also be true or false. But in conjunction, logical conjunction, we have a rule here. Only one case can be true, in which both operands, both expressions are true. So if the first expression or first statement is false and the second one is true, then we have false. But if both of them are true, then we have true. So in conjunction, logical conjunction, both expressions have to be true for you to get a true result. If even one of them is false, you'll always get false. Let's take a look at this and see. True and true, true. False and false, false. True and false, false. False and true, false. So we only have one true case here. One true result. All other results are not true. So when you use this two ampersand signs, it means that both of your statements have to be true for you to get a result, a true result. Now, let's move on to bitwise conjunction and see. Bitwise AND is a binary operator, which action is equivalent to using a logical AND for each pair of bits that are on the same position in the binary representation of the operands. What this means is very simple. I told you that we have ones and zeros for bitwise conjunction or bitwise AND. And I also want you to notice that for bitwise, we only use one ampersand sign. If we go back to our conjunction, logical conjunction, we have both ampersand signs used. So we use two ampersand signs. But for bitwise, we only use one. And it's the same thing. It has the same value and. The truth table for the operation of bitwise and conjunction of values. We have 1 plus 1, 1. 0 plus 0, 0. 1 plus 0, 0. 0 plus 1, 0. So in this case also, we always have to use both bits to be 1, 1 for us to get 1. Even if you have 1 and 0, we'll get 0. 0 and 1 will get 0. So it's just like a multiplication table, for example. Let's take 1 times 1, 1. 0 times 0, 0. 1 times 0, 0. 0 times 1, 0. So this is an example, and this is a way you can remember this. Just have to remember this and remember that we use only one ampersand sign. So here we have an idea of conjunction, bitwise and logical statements. Let's move on to the next slide and look at something else. On this slide, what we're going to look at is disjunction. We use these double vertical bars to represent OR in C# language. Disjunction is a logical operation closed by its implementation to conjunction, or in a sense of or that, or this, or both. Let me explain this in other words and you'll understand what I mean. So here again, you remember that we have these two operands. This can be true and it can also be false. This can also be true or false. Here you see our two vertical bars, meaning that either this or this should be true for us to have a result, or should be false. So here we have the table of truth for disjunction. True or true? We have true. False or false? False. True or false? True. False or true? True. What do you notice here? Do you notice that in disjunction, one of them can be true and your result will be true? In this case, if both of them are true, then we have true. If both of them are false, we have false. And if only one of them is true, we'll still get true. It doesn't matter if it's the first one or the second one, we'll still get a true result. So, contrary to conjunction, in disjunction, either one of them should be true for the result to be true. Let's move on to the next slide, and we have bitwise OR. Here you see we are using only one vertical bar. Bitwise OR is a binary operator whose action is equivalent to which using a logical OR to each pair of bits that are on the same positions in the binary representation of the operands. Here we have the same scenario, just like in our bitwise and table. Here we have the table of truth, and the table of truth for the operation of bitwise or disjunction of values. 1 or 1, we get 1. 0 or 0, 0. 1 or 0, 1. 1 or 1, 1. So in this case, it's enough for only one of them to be 1 for us to get a result of 1. It's either this or this. So either one of them can be 1 and your result will be 1. And if both of them are 1, of course you'll have 1. But if none of them is 1, we'll get a 0 result. So in this case, only one case can be false. All other cases are true. All the 3 other cases are true, just one case is false. But we don't say false here, we say 0. Where we say false is right here. You can see we only have one false. Here we have true, true, true. So in disjunction, we have false, true, true, true. Just one false where we have both of them in the false position. Then again, we have exclusive OR, or XOR, as you can see here. The sign or symbol used for exclusive OR is the circumflex. This is the sign, you can see it here, the circumflex sign. Now, exclusive OR, Boolean function, and logical operator, the result of the operation is true only on the condition that only one of the arguments is true. So, if both of them are true, your result will be false. Only one of these arguments, these operands here, each of them can be looked at as an argument. One argument, another argument, and then they give you a result. So only one of them has to be true for our result to be true. If both of them are false, we get a false result. If both of them are true, we get a true result. So here we have the table of truth for the exclusive OR. True, exclusive OR, true, we get false. False, false, we get false. But look at this. True, false, true. False, true, true. Meaning that only one of them has to be true for us to get a result that is true. If both of them are true or both of them are false, then we get a false. So this is the easiest one, I think, in all of them. Let's move on to the next slide and see bitwise exclusive OR. The same condition here. Bitwise exclusive OR is a binary operator whose action is equivalent to using a logical exclusive OR to each pair of bits that are on the same position in the binary representation of the operands. Here you have the table of truth. It's the same thing here. 1, 1, 0, 0, 0, 1, 1, 0, 1, 0, 1, 1. So only one of them has to be 1 for us to get 1. But if both of them are 1, if both of them are 1s, we can get 1. If both of them are 0s, we can get 1. We will always get 1, 1, 0, 0, 0, 0. But if one of them is 1, the other is 0, it doesn't matter which one is 1 and which one is 0, like in the position. Then we'll get a result that is 1. Moving on to the next slide, we have negation. Not something. And this, we use exclamation mark as the sign. So here what you have here is an operand. Let's say this is true. So not true will result false. Not false is true. And the truth table for negation is very easy. It's just not false, true, not true, false. This is very easy. If something is not true, then it must be false. If it's not false, then it must be true. So negation of the truth is a lie, and negation of a lie is the truth. That's all. It means if it's not true, it's false. If it's not false, it's true. There is nothing to this. It's the easiest one here. Let's move to the next slide and see binary negation. So let's take a look at how we can change the sign of a binary number. To change the sign of a binary number, it is necessary to perform its negation and increase the result by 1. What does this mean? This is the formula that we have to use. So how does it work? If you have a positive number, what you have to do is you have to take its negation, you have to change it and into the negative and then add 1, and then you'll get the same number but only in the negative form. The same thing with a negative number. If you have a number, you take its negation, you add 1 to it, and then you'll have a positive number. Let me show you in this example here. Let's say we have 1 in the decimal number, okay? Well, in the binary format, 1 is 0000001, something like this. And what you have to do is you have to change the sign. You have to change the negation. What I mean by changing the sign or negating it is if you have 0, you put 1, 0, 1, 0, 1, 0, 1, 0, 1, 0, 1, 0, 1. And then here we have 1, which means the negative of 1 or the opposite of 1 is 0. So we have 0, 1, 1, 1 instead of this. But this in a binary number means -2. So this, the value for this binary number in a decimal number, it's -2. So how do you get -1? If you have 1 and you wanted to change its sign, changing the sign means from plus to minus. So if you have 1, what you're supposed to get is -1. To get that, what you have to do is you add 1 to it. Once you add 1 to -2, what you get is -1. Simple primary school mathematics. 1, you change it. If you change the signs and you change zeros to ones or ones to zeros, you'll get -2. And you add 1 to -2, you get -1. So basically that's how to change the sign. You have to first change the binary number into the opposite. If it's 1, 1, 1, 1, you change them to 0, 0, 0, 0. If they are zeros, you change them to ones. And then you add 1 to whatever your result is, and you'll get a negation. You'll get like the opposite of what you had. You have successfully changed the value of 1 or maybe 2 or 3, whatever you tried. Now let's move on to shifts. Logical shifts. How to shift numbers in the binary format. You see this sign here. This sign here is the sign for logical shift. If it's pointing to the left, then we're shifting to the left. If it's pointing to the right, then we're shifting to the right. So we have left shift and right shift. And that's it. Here, what you have here is you have in binary format, you have the number 253. If you move 253 2 steps to the left, that's left shift 2 steps. You're going to get 244, but that's not possible. How? Well, in binary format it's very possible, and I'll show you how. This is what happens. Here, you're going to lose some numbers. Why? Because you have 253. You can see this box here. This combination of numbers means 253 in decimal format, but they are written here in the binary format. So once you move 2 steps to the left, what's going to happen is this first 2 numbers, since they are the numbers by the left, they are going to go out of this box here. And once they go out of this box, they are lost. And that's it. And there's a rule that any number that enters from the right is a 0. So when you lose 2 numbers here, of course they will have to be replaced by other numbers coming from the right. Since we moved left, that means we've given a little bit space here for people from the right to come in, or numbers from the right to come in. So since this rule says that any number that comes in from the right or enters from the right, then it's a 0. So if you have 1, 2 moved out, then we have 1, 2 spaces. So we have 2 zeros here. And if you convert this into a decimal number, you'll have 244. So that's how logical shifting works in C#. Any number that moves out of the box, rule number 1, it goes out. Rule number 2, any number that comes from the right, it's a 0. So moving out of the box means we have lost that number. Moving in from the right, it means we're getting zeros attached. Fine. So let's move on to the next slide and see. Logical shifts to the right. Let's take a look at this. In this case, we have -127, and we're moving it 2 steps to the right. And our answer is -32. But why is it like this? The same reason. You have a binary combination of numbers here, ones and zeros, and these numbers are -127 in the decimal form. So 127 in decimal looks like this in the binary format. Now, remember rule number 1. Any number that moves out is lost. So here, if we are moving 2 steps to the right, what happens is we are going to lose the first 2 numbers by the right here. So 1 and 0, they move out of the game and they are lost. We forget about them. And then look at this. On the left, if the number is positive, zeros enter. If it's negative, ones enter. In this case, our number is negative. so we are expecting ones to enter. If our number was positive, then we're going to expect zeros to enter. But since our number is negative, of course, 2 ones will enter. So we've lost 2 digits here, and 2 extra digits come in from the left. So 2 ones come in once again because our initial number was negative. So we have 1, 1, 1, 0, 0, 0, 0, 0. And if you convert this into the decimal format, it's going to give you an answer of minus 32. So basically, shifting is not subtraction, it's not division, it's just shifting. Let's go back again, just one more step and see. Shift to the left. Any number that goes out of the box is lost. Any number that comes in from the right is a 0. But in shift to the right, any number that goes out of the game, out of the box, is out of the game. We have lost that number. Any number that comes in here, it can either be positive or negative, depending on the value of our initial number. If our initial number is positive, then zeros enter. If our initial number is negative, then ones enter. And you remember that our initial number is negative, so that means ones entered, and we have minus 32. When we go into our examples and exercises, I will explain more on all these and you will see. Let's go back to the beginning. Conjunction, you remember, double ampersand signs. Here we have operand 1 or operand 2. We have basically 2 arguments. They can also be called arguments. Argument 1, argument 2. Double ampersand signs here mean that this is AND. Operand 1 and operand 2 gives you a result. Table of truth for conjunction. Logical conjunction. We have true and true, true. Every other thing is false. Bitwise, you remember that we just use 1 ampersand sign. And we also have one case in which our result is 1. All others are 0. Now, move to the next one. Disjunction OR. We have 2 vertical bars. Argument 1 or argument 2 is equal to our result, which means argument 1 or argument 2, true, 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 false, 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 true, false, true, false, true, true. So either this or this, either this or this. In conjunction, both of them must be true for you to get true. But in disjunction, one of them is enough to give you a true answer. For bitwise disjunction or bitwise OR, the same thing. The only difference is we use 1 vertical bar instead of 2. And we have 1 or 1, 1, 0 or 0, 0, 1 or 0, 1, and the same thing goes on here. Now, let's see what else we have. We have exclusive OR. We use the circumflex, you remember. First argument, second argument, and our result. True, true, we get false. False, false, false. True, false, true. False, true, true. In this case, if one of them is different, then we get true. If both of them are the same, then we get false. Next, we looked at bitwise exclusive OR. The same thing. 1, 1 will give you a 0, 0, 0, 0, 1, 0, 1, 0, 1, 1. So one of them has to be different from the other, and then we'll get an answer of 1. Negation, you remember, not sign. Not operand is equal to result. Not false, true. Not true, false. How easy is that? Let's move next. We've moved to the next. You remember the tilde sign for not in bitwise negation. Not 0 means 1. Not 1 means 0. And that's it. That's as simple as it can get. Change of sign, remember this, it's very important. First, it's necessary to perform its negation, then increase by 1. So we have 1 here, and we get the opposite of 1. Each 1 here becomes 0, 0 becomes 1, and we change their signs here. After this, we add 1. After changing the numbers to their opposite, after getting the negation, you add 1, and then you'll get the same number you had, but just with a different sign. And that's it. Next slide, we have shifts. Shift to the left, 2 rules. Bits that go out of the box are lost. Bits that come in from the right hand side are always zeros. Shift to the right, 2 rules also. Bits that go out are lost. Bits that come in from the left are either positive or negative depending on our initial number. If our initial number is positive, zeros come in. If our initial number is negative, then ones come in. And that's simple. Okay, so now that we have seen the presentation, let's start looking at the examples and see what we learned today. Remember, we learned conjunction. Now, in conjunction, it's like this. The truth table for the operation of conjunction, you remember this ampersand sign, meaning and there is a rule. If one of the operands is 0, the whole structure is 0. Otherwise, 1. So, this is the truth table for conjunction. Remember, 0 and 0, 0, 0 and 1, 0, 1 and 0, 0, 1 and 1, 1. So 1 is a result that we can only get in one case out of these 4 cases. Let's take a look at this example. Here we have in line 23 an operand, a variant operand, and we assign a value of 255 to it. This is in the decimal system, okay? 0x means the hexadecimal system. So 0xFF is 1111, 1111 in the binary system, and FF in the hex system, and 255 in the decimal system. Operand 2 is 01 in the hexadecimal system. So 01 in the hexadecimal system is 00000001 in the binary system, 01 in the hexadecimal system, and 01 in the decimal system. So basically 1, 1. The result here of operand 1 and operand 2 will be something like this. You have operand 1, which is 255, and operand 2, which is 1, both in decimal system. The result is going to be 1. But how? This is how. If we put them one on top of the other, just like we have them here. Remember that 1 and 1 is 1. So 1 and 1, we get 1. 1 and 0, we get 0. So 1 and 0, 0, 1 and 0, 0, 1 and 0, 0, and so on. So our result will be 1 0 0 0 0 0 0 0, and this number in the binary format means 1 in the decimal format. So this is basically how conjunction works. Now let's take a look at disjunction. In disjunction, if one of the operands is 1, the whole structure is 1, otherwise 0. So if one of them is 1, then we have 1. 0 or 1. Well, 1 is 1, so 1. 0 or 0, 0. 1 or 1, 1 or 0, sorry, 1. 1 or 1, 1. So here again we have two operands, operand 1 and operand 2. Operand 1 is 2 in the hexadecimal format. operand 2 is 1 in the hexadecimal format. Our result of operand 1 or operand 2. Now, here again we have the equivalents in the binary format, the equivalents in the hexadecimal format, and the equivalent in the decimal format. So, let's do it like this. 0 and 1. We look for 0 and 1. We get 1. So we put 1. Next we have 1, 0. So we look for 1, 0. We have 1. So we put 1. The other ones are 0, 0, 0, 0, 0, 0. So let's just put them 0, 0. We have 0. So we put all of them here and the rest are zeros. And this number here, this combination of numbers, is equal to 3 in the hexadecimal format and 3 in the decimal format. So of course the result is 3. So if you run this program, let's run it and see. You see 255 and 1 is equal to 1. 2 or 1 is equal to 3. You see what we have here? 2 or 1, this is what we have here. 2 or 1 is equal to 3. Let's move on to the next example. Let me just collapse this and go to exclusive OR. In exclusive OR, what we have is if the operands have the same value, the result is 0. If the operands are different, then the result is 1. So 0, 0, 0, 1, 1, 0, 1, 0, 1, 0, 1, 1. Here we have two operands here, 3 and 1, both in the hexadecimal format. And we're looking for the result of operand 1 exclusive OR operand 2. So let's try it. 1 and 1. We look for 1 and 1. Our result is 0. We write 0. Next we have 1 and 0. So we look for 1 and 0. Our result is 1. 1 and 0. Result is 1. The rest are zeros, all of them. So we look for 0 and 0, 0. And we just write our zeros here. So in the binary format, this is 2 in the hexadecimal format and also 2 in the decimal format. Let's collapse this and look at negation. So what do we have in negation here? What we have is the truth table for negation. Not 0 is 1, not 1 is 0. So operand 1 is equal to 1 in the hexadecimal format. And this is our 1 converted into binary system and 1 in the decimal system. So our result is equal to not operand 1. How do we do this? If it's not 1, then it's 0. If it's not 0, then it's 1. If it's not 0, it's 1. If it's not 0, it's 1. You continue like this until you get the result. And this in the binary system means -2 in the decimal system. So once again, if we run our program, you remember 3 exclusive, 1 is equal to 2, and now we have not 1 is equal to -2. So not 1 is -2. Next, let's look at change of sign. To change the sign of a number, it is necessary to negate it first and to increase it by 1. So this is the formula. Let's look at how it works. In line 90, we have an operand, operand 1, which is equal to 1 in the hexadecimal format. This is the equivalent in the binary format. We want to change the sign of operand 1. So how do we do this? First, we negate it. Negating it means we change from 1, we get 0, 0, we get 1, 0, 1, 0, 1 is just like the opposite. If it's not 1, then it's 0. If it's not 0, it's 1. If it's not 0, it's 1. Just the same thing we did here, okay? So now that we have negated it, what we do next is we increase the result by 1. Now, remember this 2 plus signs, it means increase something by 1. In this case, we are increasing our result by 1. So when you increase this by 1, what you will get is you just have 1, 1, 1, 1, 1, 1, 1, 1, 1. And if you run this program now, you will see that our result is -1. So this is basically how negation, change of sign, exclusive OR, disjunction, and conjunction work. Let's move on to exercise 2 and see what we have there. Moving on to the next example, let's take a look at the practical application of these two operators, the ampersand operator and the OR operator. Remember, this is AND and this is OR. So here we have an example. We have an input-output port or a register with a particular value in it. We need to turn on a device managed by the first bit, setting the first bit to 1. Then we need to turn off the device, resetting the first bit to 0. Let's take a look at our initial value here. The value of our port is 00001111. If you remember, when we had light bulbs representing bits, we know that 0 means it's off, 1 means it's on. So here we have 4 switches on and 4 switches off. But then we're asked to switch on the first bit. Switching on the first bit is very easy. We just need to change this 0 to 1. But then we don't want to touch all these bits here. All these, let's say 1, 2, 3, 4, 5, 6, all these 6 bits, we don't want to touch them at all. So we only change the first bit. Now, how do we do this? What we have to do is, first we write our initial value of the ports. The initial value is F0, which is in the hexadecimal format. In the binary format, this is how the computer looks at it. But we don't want to be writing ones and zeros, so we just write F0 in the hexadecimal format. So in line 18, we created a byte-typed variable named port and assigned the value of our initial port value here. Next, we need to create a mask. This is where we need to be creative. We need to create a mask that will not alter the condition of the first 6 digits here. These guys, we don't want to change their condition. We only want to change the state of these two. So if we want to change the state of this 0 to 1, what we have to do is we have to create a mask, but we don't want to touch this. So how do we do this? Before I tell you how to do it, let me tell you what a mask is. A mask is basically like something you put on another thing to change the way it looks. Basically, we all wore masks when we were kids. Now, here, what we are doing is we're taking this mask, we put it here, this mask we created, and then we hope not to change the value of the initial 6 bits that we have here, but to change the value of just the first one. What we need to use is we need to use the OR operator. Why do we need to use the OR operator? Because if you remember, in the OR operator, let me just go back to the slides and show you in the presentation. Here we go. Now we have 1 or 1 is 1. 1 or 0 is 1. 1 or 1 is 1. 0 or 0 is 0. So Using this, we know that if we have 1 and 0, it's still going to be 1, so we are not going to change anything here. The value of this 1 will not be changed. And we know that we only have one case in which we'll have 0, which means both of them have to be 0. So let's go back to our exercise. Here, what we can do is we can put all zeros and then put 1 where we need to change the value of this 0. We know this is switched off, so if we put 1, it's going to be 0 and 1, which is 1. Let's take a look at it back here. 0 and 1, which is 1. So we have successfully switched on this without tampering with the state of these ones. This is 0, we add 0, it still remains 0, we haven't affected it. 0, 0, we haven't affected it. 0, 0, 0, we haven't affected it. 1, 0, 1, 1, 0, 1. So in this result here, what will change is just the 1 here. You see, we have practically the same thing here and the same thing here. The only difference is here we have 1. So it means now this device has been turned on. So this is how to use the OR operator to switch on a device. Next, in line 21, we write console write line, and we assign the value of the new port to our port, the masked port. So let's look at this. Here we have 0 and in X. What we are doing is here we have the value in byte, but what we need is we need the value in the hexadecimal format. So if we run this program, F5, you will see that the console will write port is equal to F0. Port is equal to F0. So basically, we're taking this value of the port here and putting it in here in the hexadecimal format. And then we're telling the console to write the value, that means this value, to write it in the hexadecimal format. And here it has written it for us. Next, what we do next is we apply our mask. Now, port, which of course we know the value of port is F0 in the hexadecimal format, we assign it a new value here. The new value here, this operator here, means we have port or mask. So port or mask. What we are asking it is to display this result. So this computer now will quickly somehow calculate this. This is how it will calculate it, and then convert it into a byte and assign it a new value. Then it will just hold that new value. Now, converting it into a byte, this is what you will get. But we don't want this to be displayed. What we want is we want it to be in the hexadecimal format. So we write something else here. We write console write line, and we assign the value of this port now, this new port. We assign the value and we convert it into the hexadecimal format. This 0x here means we need the value in the hexadecimal format. So what will happen is it will display this, but in the hexadecimal format. Now let's run this and see. Here we have port has a new value, F2, which means now the port is active. It's up and running. But next, we have our port, we have our mask, and we've applied our mask. We haven't tampered with all the other devices. We just tampered with the first device, but we need to turn it off. Now, we've turned it on and we need to turn it off. To turn it off, what we need is we need to create another mask. Now, this is the initial value when it's on. So now we have our on value here. This is how our bit looks like when it's on. It's 1, but we need to change it to 0. And if we use the OR operator and put zeros here, it's not going to change any value. It's just going to leave it as it is. So we go back to our AND operator. Now in this AND operator, what we have is we have 1 and 1, 1, 0 and 0, 0, 1 and 0, 0, 0 and 1, 0. So basically we only have one occasion when we'll have an ON situation. It's only when we have 1 and 1. All the other cases will not temper or will not affect our devices in any way. So what do we do here? What we do here is we use the AND operator. You can see it here, AND operator. Okay? Because we need to have 1 and 1. We need to get 1. What we need to do actually is to return it to this position. We need to return it to the off position, the initial value that was given to us at the beginning without any mask. So we have 1, 1, 1, 1, and we put 1, 1, 1, 1, because in any case, since we know that the AND operator, which we have here, is not going to change the value of 1 if we put 1, so we have 1, 1, 1, 1, 1, 1. All of them are in ones. Here, all of them are in zeros. The only difference is here we have a 1 to switch on this very device, and here we have a 0 to switch on this very device. So if you need to switch off, you use the OR operator. If you need to switch on, you use the AND operator, and where you have the device that you want to switch on or you need to switch off, you can have either 1 to switch it on or 0 to switch it off. Alright, so when we apply this AND mask, what we will see is we will see that we have 1, 1, 1, 1, 0, 0, 0, 0 back to the initial value. But we don't do this. This is just to explain this case for you. We don't use the binary system. What you just need to do is you need to create a mask. This is where we created the mask. You can see new mask, or you can say mask 2 if you want. I just called it a mask, and that's all. And of course I can do that. I assigned the value of FD in the hexadecimal format to my new mask. This is how FD looks in the binary format. You don't need to know this off heart. What you need to just know is FD for your very system. But every system varies. It depends on which switch you want to turn off or on. In our case, this is what will work for us. So, in line 32, we assign the value of this operator to our port, the new value, which means we want to use this value and assign it back to the port. So, we have port and mask, which means port and our new mask, and we need to convert it into a byte and then somehow assign it through this assignment sign to our port. And we ask the computer to write the value of port, our new port here, in the hexadecimal format. The computer should convert it into the hexadecimal format and then assign it to the port. So if we run this program, what we should see is F0. It should go back to the initial value. And here you go, F0, which means here it was off, we switched it on, and then we switched it off again. So this is like how you can switch on and switch off devices using the AND and OR operator. Let's move on to the next exercise, and I'll show you how to encrypt data. So let's take a look at how we can encrypt and decrypt messages. Here, what we have is, using XOR operation, we can encrypt a message. You remember what XOR is with this sign that I told you, circumflex sign. Now, before we go any further, I would like to explain what encryption and decryption mean. Encryption is basically locking your message with a key. If you want to send a message to somebody and you don't want the message to be intercepted and read, what you do is you encrypt it. You put a key and you lock your message. then you can send just the message, and the person receiving the message there, you can also send a key to the person. He will take the key, open the message, and read your message. In case somebody somehow intercepts your message, he has the message but he can't read it, except if he can hack it. So that's why we have cryptographic strength. Cryptographic strength is the strength of your, let's say, password or your key, which of course can be increased by increasing its length. So the longer your key is, the stronger the key is. And it will be more difficult, of course, to decrypt or to hack into your message. So, that being said, let's look at how we can encrypt a message. This is a very simple example, and we are using the same key for both encryption and decryption for simplicity only. Now, in line 16, we created a variable here, ushort typed variable, and we assigned a value of 0x008828. Now, this 0088 is in the hexadecimal format. That's why we have this 0x right here. So, remember that ushort has a 16-bit length. So, why are we using ushort? First of all, we are using ushort because our message, which is this A here, is a char type. And char, of course, you remember, we use 2 bytes to save char symbols. So this A here represents a char type character, and it has 2 bytes in the Unicode format. Here we created a character, a char typed character, and assigned a value of A to it, and we know that the value of A here is like 2 bytes. That's why we need to create a ushort typed variable here, which is our key. It's also 2 bytes. So here you have 16 bits. Of course, each byte has 8 bits, so 8 times 2 will be 16. Fine. Now, in line 19, we ask the console to write this operation for us. But it's just going to write this, and it has to calculate this, and then put them right in here. If you remember, we've done something like this. 0 and 1. It will take character, which is here in the 0 position. It will put it in 0, and it will take byte character and put it into 1. Here we have 1x because we want our result to be in the hexadecimal format, not in bytes. If you now run this program, so far what you are going to see is your character, and we go back to our character, which is A. So source symbol is A. Its code in the code table, here we have character, which is A, converted into byte. I'll just tell you that the code for A is 41. So we should see source symbol is A, its code in the code table 41. Fine. Next, we ask the console to write this also. Size of symbol, and we take character, we put it here. Then size of char multiplied by 8. So size of char is 2. 2 multiplied by 8. Here we know we have 16 already. So 16 is going into 1, and size of symbol character is going into 0. So let's run this program and see if it works so far. F5 to run your program. And here we go. Let me just zoom this out a little so that you can see. Here we have source symbol is 0. So 0 here, I told you are going to take character, and character is A. So source symbol is A. Its code in the code table is 41. I told you that the code for A is 41. Size of symbol A is equal to 16 bytes. Here we have size of symbol 0. Character is A. So we take character and we put it here. That means we're taking A and we're putting here, and that's why we have A here. It's equal to 16 bits. 16, I told you that size of char is 2 bytes. So we have 2. 2 multiplied by 8, 16. So we have 16 bits. Fine. Let's close this and go back to our lesson. Here, the encrypting stage or the encrypting block. In line 23, what we are doing, let me zoom out a little so that you can see what we're doing. In line 23, we're asking the character to be assigned the value of char, and here we have open and close parentheses, character and XOR, exclusive OR, secret key. So we are encrypting our message by carrying this key and applying it to our character, and we bring it out in char format. So if you do this, what will happen is it will take A, which is here, and our key, which is 0088. Now our key is in U short, our A is in char. It will now convert everything to char and then apply it or assign it to a character. So we'll have a new character here. Then console write line. Now this is what somebody will see. The encrypted symbol is now this character, not this character, but this is now the encrypted symbol, our new character. So we have something here. Its code in the table is, and we'll have something here. So we're taking this character, which is here, and we're putting it into 0, and then we're taking the character, convert it into bytes, and then put it here, and here we'll have it in the hexadecimal format. So you can see how difficult and how crazy the thing might sound, but it's very, very easy if you just look at this and understand it. Here our character was our initial character A, character still the initial character, but here it has changed to this new character, which is a combination of our character and our new key, the key that we just created. So let's run the program and see. F5. Here what we have is the encrypted symbol is E. Its code in the code table C9. So in the code table, E here is C9. But notice that E has something right above it here, and this is like an encrypted system. I wouldn't want to go very deep into explaining this. I just want you to know how to encrypt and decrypt messages for now. So after encrypting our message, we can now send the message on its own and send the key using a different method or different way, so that even if our message is somehow intercepted, nobody can read it. But if the message reaches the receiver and he has the message, but he now needs a key to open it, so we have to send the key, and we've sent the key. But how does this happen? How does the key open the message? What is the program? What is the code for that? Now in line 27, we have character, and we assign the value of this operation to our character. To just bring out our original character, we need to assign this value to it. What we are doing here is we are taking our character, which is this now, the encrypted character E, and apply the key, which is 0088, and then using this XOR, we somehow connect them, convert it into char, and then assign it into this character. So what am I trying to say here? I'm trying to say that using XOR, what you can do is you can apply a key to a certain character, and using the same XOR, you can apply the same key to decrypt it. Encryption with the same key, the same XOR. Decryption, same key, same XOR. It's not always like this, but this also works. This is just like a simple example, and this is where everybody starts from. So console write line. The decrypted symbol is what? Now we're going to have A. Its code in the code table is byte, character converted into byte, and will be put here, and then here it will be converted into the hexadecimal format. Our decrypted symbol will be A. Let's step this program and see. F11 to step your program. Now you can see what I've been telling you. Here we have this character, which is A, and we are putting A into here, and when we move into here, we have A and 65. 65 means A in bytes when it has been converted. If we step down here, what we'll see is the value of our character is still the same. It is A, and the value of char here will be 16. You can see it right here, the value of our size. So char is 2 and 8, so 8 times 2 will give you 16. Alright, now here you can see our character. Let's just step this down a little. Our character here has been changed to E. We have it E here. Why? Because we have applied our key to it. Now, after applying the key, when we move down, we'll see our character here is still E, but when we go out, our character has changed back to A, its initial value. So this is how this works. And you can see, of course, the decrypted symbol is A, which is our initial symbol. Its code in the code table is 41. 41, 41, AA. So we have encrypted it and decrypted it. Very easy and very simple example. Let's move on to the next exercise. In this example, we're going to take a step back and remember conjunction, disjunction, exclusive OR, and negation. Now, in line 11, we created a bool-typed variable named operand 1 and assigned a value of false to it, and operand 2 assigned a value of false to it too, and result applied a value of false to it. So remember, bool can be either false or true. Now, if we go down to our conjunction, you remember we had a table of truth for the conjunction here, and here we have created in line 23 an operand 1. We assigned a value of true to it. So operand 2, we assigned a value of false to it, and result, we want the result to be operand 1 and operand 2. What happens? It will take true and false is equal to what? Let's go back to our presentation and I'll show you that very fast. True and false is equal to false. So here we go back and we run this program and see if it will give us false. Here we have it. True and false is equal to false. Very easy. Now, this is just like a way we can do it. Console write line 0 and 1 is equal to 2. And then we write operand 1, which is true, operand 2, which is false, and result, which is false. We know it already. We have seen it. So result will be put in 2, operand 2 will be put in 1, operand 1 will be put in 0. Remember the indexing, everything is still the same, and we're doing the same procedures for all of them here. Alright, let's move on to the next one. Let me just collapse this to make it easier for us to see. The same thing here. Just here we're using the OR sign. Table of truth for the OR is right here for you. We don't have to go back to our presentation all the time. I think we have it here and everything is okay. Operand 1 is true. Operand 2 is false. So, result, we need a result, operand 1 and operand 2. What do you think will happen? It will take true or false. So, true or false. What we should expect is true. We have it here, true or false, true. So, console write line 0 or 1 is equal to 2. So we're assigning the value of this operation to 2. 1 is true, we put it here. 2, operand 2 is 1, and we put it right in here. So true here, false here, and we need a result here. This result will be put in here. And we know, of course, that we're going to get true. Let's run the program and see. true. So you see it works. Going on to the next example, what we have is exclusive OR. Once again, table of truth for the exclusive OR, and in line 60 we assign a value of true to operand 1, assign a value of false to operand 2, and we need a result using the exclusive OR sign. So true, exclusive OR, false. What we have here is true, exclusive OR, false, and we should see true if we run this program. Again, here the same procedure. We take this value of operand 1, we put it into 0, take the value of operand 2, put it into 1, and the result we put it here. Let's run the program. We have true. It works too. And our rule is right. Negation. Well, I guess this is the easiest of them all. You have, if it's not true, it's false. If it's not false, it's true. That's the rule. And it's a global rule. Everybody knows it. It's very logical. So operand 1, we assign a value of true to it. And we need a result of this operation. So we assign the value of this operation to result. If it's not true, guess what? It's false. So not true is equal to false. Taking operand 1, which is true, put it here. Result, false, we put it here. We should have false now when we run the program. It's false. It's not true, it's false. I told you it's the easiest one. Let's move on to the next exercise and see. So let's take a look at how we can check a conditional statement using the AND operator. Here, for example, to check the conditional statement A is less than X, which is less than B, we cannot write it like this. If you write it like this, the computer will not understand you. Why? Because you need to have two operands for each statement. And here we have just 1 and 1, which is not correct. So how do we write it in the correct way? Here is how to write it in the correct way. If you open and close parentheses, and within this open and close parentheses, A is less than X and X is less than B, then do something. Else do another thing. You remember conditionals, yeah? So let's take a look at this in practice. In line 16, we created an int-typed variable named A and assigned a value of 0 to 8. We also created B, assigned a value of 5 to 8, and X assigned a value of 3 to 8. So now we go into our conditional statement. This is our conditional statement here, right here. If A is less than X and X is less than B, then console write this line out. So console write line number 0 is in the range of numbers from 1 to 2. But this is not 1 and 2, and this is not 0. What we are asking the console to do is to take the value of X and put it here, which is 3. So number 3 is in the range of numbers from 1, which is A, and A is 0. 0 to 2, which is B, and the value of B is 5. So what we should see is number 3 is in the range of numbers from 0 to 5. Let's run this and see. You will notice that I run programs at each stage because I want to make sure that it works first before going on. You would want to also practice this. Why? Because you don't want to write a lot of things and then find out you've made a mistake somewhere in the beginning or in the middle of your code. So let's run this program and see. So here we have number 3 is in the range of numbers from 0 to 5. It's correct now. Then we can go on. We create the else conditional type here. In line 20 we have else, and in the body of else we have console write line. Number 0, which we know is x, so number 3 is out of the range of numbers from 1 to 5. From 0 to 5, sorry. Because A is 0 and B is 5. This will only be run in case our x, which is 3 here, is more than 5 or less than 0. So now let's run the program again and see. Right now, because 3 is in the range of 0 to 5, it's written like this. But if we change the value of 3 to, let's say, 6, what will happen is this case is no more correct. So we need to go into the next stage, the else stage. And in the body of else stage, of course, we'll see number 6 is out of range of numbers from 0 to 5. Let's run the program. And here you go. Number 6 is out of range of numbers from 0 to 5. Very easy and very useful application. Now in this example, let's take a look at logical shift. You remember in our presentation, we explained logical shift. We can have a shift to the left and a shift to the right. Very good. So here in line 11, we created a byte-typed variable named operand and assign a value of 81 in the hexadecimal format to it. And 81 looks like this in the binary format, 10000001. So next, we print out this message to the screen. But we're not going to see 0x. What we're going to see is we'll see the value of operand put in right here. And we know the value of operand is 81. So let's run this program first of all and see if we'll get number before shift 81. Number before shift 81. So we have succeeded in taking the value of operand and putting it right in here. Now we need to change the value of operand. We need to move 2 steps to the left. So in line 16, we assign the value of this operation to our operand. Now we're trying to change the value of our operand, and it will have a new value, which is the result of this operation. What do we have here? First of all, you see byte here. It's a type of like explicit conversion. And we're taking the value of operand, shifting it 2 steps to the left, and then converting it to bytes, and then assigning it to our operand. So now if we shift the value of operand, which is 81, and you can see it here in the binary format, if we shift it 2 steps to the left, what we'll get is something like this. Why are we getting 000100100? Why? Because you remember that if we shift it to the left, what will happen is we'll lose some numbers here. Some numbers will go out. And in this case, 2 digits will be lost. They will go out of the range. Why? Because we're shifting 2 steps to the left. And remember, when we're shifting to the left, all the numbers that come into the right are zeros. So here we've lost 2 numbers, meaning that 2 extra numbers will come right from the right hand side. And the numbers that will come in are zeros. So we have 2 extra zeros here. We've lost this and we've gained 2 zeros. Now we write in line 19, console write line, and we want to print out the value of our new operand right in here. Now we have changed the value of our new operand and assigned the value of this operation. So this operand now has the value of this operation, which is this in the binary format. So what we are doing is number after left shift, and we should have something here. And what we are going to get here is the value of this operand. It's going to be this here and put in here, but we need it in the hexadecimal format. That's why we have OX here, because right now here it's in the binary format. So let's run this program and see our result. Number after left shift is 4. So this actually is 4 in the binary format. In the hexadecimal format, it's 4 like this. In the binary format, it's 0, 0, 1, 0, 0, 0, 0, 0. So this is the equivalent of 4 in the hexadecimal format. Now, how about a left shift? We have finished a left shift. Now let's look at the right shift. Again, we take the value of our operand and we assign this value to it. What is this? This is the value of our operand, and one step to the right, and then we assign it to our operand. So what happens here? What happens here is we get to lose one number from the right. So what we are doing is we lose one number here. Sorry, right here. We lose one number here, and now we have 0, 1, 0, 0, 0, 0, 0. And what will happen is on the left, if the number is positive, zeros enter. If negative, ones enter. But we know our number is positive, 4. So 4 is a positive number. That's why what will enter is a 0. A 0 will enter from the left. So we've lost this number here, and we'll have an additional 0 right here. So we have 0, 0, 0, 0, 0, 0, 1, 0. It's very easy. If our number were negative, what we'll have is we'll have 1 coming in from the left. But our number is not negative, it's positive, so we have 0 coming in. Console write line. Now let's see the value of this in the hexadecimal format. We want this message to be displayed, to be printed on our screen, and we'll take the value of whatever we have here and put it right in here. Let's run it. Now you can see number after right shift is 2. So this is 2 in the binary format, and 2 of course will be written here in the hexadecimal format. Very simple. Now let's go to the next example and just look at a very, very important and interesting application of shift to the left or shift to the right. Main window. Let's just go to the main window, and here you have a type of window here. It says test. So basically what this will do is it will test the level, the visual level of your video card. If you have an integrated video card, or maybe you don't have a video card, or you have a fully accelerated video card. So let's just click on this, and you will see that it has been highlighted. Nothing is happening. The code is written right down here, and you have text block provides a slight control over displaying small amounts of text. You have vertical alignment and horizontal alignment, padding. You can read this if you're interested. It's very interesting too. But what I really want to show you is the interesting part. So you double click on test, and what you should have is 1 minute. What you should have is the code. So the code comes out, and you just scroll it up, and here what we are going to see is you'll find out that in line 17 we have tbresult.text. We sign level of visualization n. What is this n? This n is going to be a number. It can be 0, it can be 1 or 2, and you will see what they mean very soon. Now, render capability. Windows Presentation Foundation allows applications to query the current level of rendering. Rendering is just like generating an image from something else. Like you have an initial image and you generate it maybe from a lot of files, and you join them together and you generate one image. Okay, you take a lot of files or maybe pictures and you join them together and you generate one image. So render capability.tire gets a value indicating the rendering of the current thread. You'll see what I mean by value here. This value is going to be this n. It can be 1, it can be 0, it can be 2. So here in line 22, what we have done is we've created an int-typed variable named rendering tire and assigned render capability.tire, and we shift it by 16 to the right. The value of int32 high word, which corresponds to the rendering of the current thread, 16 and 17 bits. So basically the value we're looking for is somewhere in that int typed variable, which is on the 16th and 17th bits. And you remember int typed has a lot, it has like 32 bits. So what we just need is the 16th and 17th. We don't need to see 00000 a lot of times. For example, 0001, for example. We don't want to see that. Or 0000 or 0002, whatever. What we just need is we need it to be in one figure, one digit, either 0 or 1 or 2. So that shows that we have to shift to the right, whereby having zeros come in, and we'll just have 00001, and we can take those off and we just have 1, and that's it. So take a look at what I'm just talking about right now. You have 0000001. What we need is somewhere here. Let me just scroll this. Let me just zoom this out and show you what I mean. You do remember that an int has 32 bits. 32 bits meaning that we have 4 here, 4 here, 4 here. Each of these zeros represents 4 bits. So 32 bits in all, but each one of them represents 4 bits. So 4 times 8, the number of zeros we have here, is 32. But you don't want to see 0000000 and then 1 somewhere here. You see? Or in this case, we have all zeros and we have all ones. This is not very comfortable. We just want to have 0, 1, or 2. So that's why we need to shift by 16. So when we shift by 16, what we are doing here, since each one of this is 4 bytes, we have 4 bits, sorry, 4, 8, 16, and 20. So we have 4, 8, 12, and 16. So we want to shift by 16 to the right. Let's say we remove this to the right, and you have what? All you have is 1 now here, right here. All the rest will be zeros, which can be removed. The same thing here. If we remove this 16 bits, we have 0, and we put our 0 here. Same thing here. 1, 2, 3, 4 go out, and we have just 2, because it's a positive number, and anything that is coming here is 0, anything that is coming from the left. So what do these numbers mean? Level of rendering. 0 means that we have no hardware application or no hardware acceleration. So if you don't have a hardware acceleration, what you have is 0. If you have a partial graphics hardware acceleration, you'll see 1, meaning that your computer has some kind of partial graphics hardware acceleration, or sometimes called integrated graphics card. In line 32 we have 2, which means rendering of level 2 means that most of the graphic capabilities of Windows Presentation Foundation should use the hardware acceleration, and This means that you have a hardware acceleration. You have a good video blaster, good video card. So let me zoom this out a little now that we understand why we're shifting to the right by 16. Let's go down and see what we have here. Here we have a conditional statement. In line 50 we have if rendering tire is equal to 0, which means if this is our result, then write this: video card does not provide hardware acceleration. If it's 1, video card provides a partial hardware acceleration. If it's 2, video card provides full hardware acceleration. So this is basically, we're asking it to write this, to write something on the screen, to print something, not in the console, since we don't have a console here, so it's not console, but we're asking the system to write this in our box or in our table. So let's run this program and see what comes up. You see here, it's not a console application, it's a Windows Forms application. So if I press test here, I will see if I have a video card or if I don't have a video card. I suggest you do the same thing right now with me, and you'll find out if you have a good video card or integrated video card, or maybe you don't even have a video card. I doubt that, because almost all computers now have video cards. Level of visualization: video card provides full hardware acceleration. Now I can write anything I want here, of course, and it will just show this is just a program, so you can write whatever you want to here. And if you need more information about this, you can just go in right here and click this. You'll find a lot of information there. Let's move on to the next slide and I'll see. Next example, sorry. Now let's take a look at short circuit calculation. The technique works as follows. If the first operand in the operation AND is false, the second operand is not calculated. Because the first operand is false, and meaning in any case the second operand or the statement in full will be false. Now we've learned this already, we've seen it in our presentation, so I'll just go back to our presentation very fast and show you the table of truth for AND. If we go back, what we have here is if the first operand is true and the second operand is true, we have true. But if the first operand is false, in any case we're going to have false, false, false. So false, false. It doesn't matter if the second operand is true or false, we'll still get false. The only thing that matters is we have to have true and true. So, but this is conjunction. Let's go back to our short circuit and see how the same principle is applied. Here in line 15, we've created an int type variable named min value and assigned a value of 1 to it. And in line 16, we created another int typed variable named denominator and assigned a value of 0 to it. In line 17, we created another int typed variable named item and assigned a value of 2 to it. The condition, which works with the use of technique of short circuit calculation, if this statement is calculated completely, the division in the second operation or the second operand would generate a dividend by 0 exception. So here we have our condition. If denominator is not equal to 0, remember this is not and this is equal, so not equal to 0, and item divided by denominator is greater than minimum value, then write this or print this for us. Else, if this condition is not met, we go into the else block. Okay, so let's take a look at this before we run the program. Denominator, we have 0, and here if denominator is not equal to 0, meaning that this doesn't matter. We're going to the else block. We can't be in here because right from the start our denominator is equal to 0, and here the condition is it can't be 0. So we can basically forget about the if block and go into the else block. But let's start the program and just see what will happen. We are in the else block. So of course we're in the else block because we can't be in the if block. Our denominator here is not equal to 0, but here it's equal to 0, so they don't match. Now, how can we make this work? We have to read this very carefully and match our values here to what this can take in. Let's take, for example, let's say that our item is 4, our denominator is 2. Okay, let's try it now and see. We are in the if block. How did this happen? It's very easy. Denominator is 2, so denominator is not equal to 0. We have passed this test. We can now go into this test. Item divided by denominator should be greater than minimum value. So item is 4. 4 divided by 2 is 2. And 2 is greater than our minimum value, which is 1. So of course we've met our condition, and we can now safely say that we can go into the if block. Okay? So let's move on to the next example, and I will show you that using this system, using this short circuit calculation, you can calculate something like this if the denominator is at the beginning. After if, basically because the AND operation starts calculation from left to right. But in the next example, we'll not have the denominator here, and the AND calculation will not be from left to right, it will be from right to left, and it will not work. Let's just go to exercise 9 and see. Short circuit calculation technique works as follows. Of course, we know how it works, but in this case, we have the same values here, 1, 0, and 2. You remember. The condition does not work using the technique of short circuit calculation. Why? Because the operation AND is calculated from left to right. And here you can see we have item, denominator, this, and then we have the denominator at the end. First we have item divided by denominator is greater than minimum value, and denominator is not equal to 0. Whilst if we go back to the other example, we have if denominator is not equal to 0. So basically we should have this AND here because the computer starts calculation from left to right. Whilst in this example, what we're asking it to do is to calculate the other way, and it's not going to work. So if we run this program, nothing will happen. It will not run this nor this. Let's run it and see. You can see it's even showing us an unhandled exception of type system occurred in short circuit whatever. So here, let's just close this and bring it back. You see nothing has been printed. We're not going to see anything here. So this will not work. When you're creating things like this, make sure that you start from left to right. Your AND operation starts from left to right. So let's move on to the next example. Let's just collapse this and move to the next example. In this example, we're going to take a look at conversion of logical variables according to the theorem of De Morgan. You'll see a lot of confusing text here, but please don't worry, there is a logical explanation and I'll explain and you will understand. Now, let's read the text. To use De Morgan's theorems in the logical operators AND or and a pair of operands, we need to two operands, replace AND for or and or for and invert all the statement. So here we have like the rule here. This is like a table or a rule, and it states that not A and not B is equal to not A and B. So this shows that this value here that we have is equal to this value, and this one is equal to this one, and so on and so forth. So having this table at our disposal and this law, we can say that the negation of a conjunction is the disjunction of the negations, and the negation of a disjunction is the conjunction of the negations. That is true in De Morgan's theorem. But now, let's see how we can practically prove that. In line 29, we create a bool-typed variable named A and assign a value of true to it. In line 30, we created a bool-typed variable 2, assigned a value of false to it, and named it B. So here we have two conditions. Condition number 1, which is in line 33, is before applying De Morgan's theorem. And condition number 2, which is in line 36, is after applying De Morgan's theorem. If De Morgan's theorem is correct, what we should see is the same answer. If the answer here is true, that means it will be true here. If the result here is false, it means we'll see false here. So let's see how it works. Here we have not A or not B. And what is not A? Not A is not true. So if it's not true, it's false. So we have false, or here we have not B. So not B is what? Not B is not false, which means true. So not false is true, not true is false. So we have true or false. Okay, so if we go back to our table, we'll see the value of true or false. Let me take you back to the presentation and show you the table of truth for disjunction. This is the table of truth for disjunction. So we have true or false, false or true. Both of them will give you true and true. So what this means is we have not A, which is not true. It means it's false. So what this means is that we have not A, which is not true. If it's not true, it's false. So first we have false, or not B, which means it's not false, it's true. So we have false or true. Let's go back to the table and look for false or true. False or true means our answer should be true. So we can now safely run the program and see if we're correct or not. False or true should be true. Not A or not B is equal to true. Now, if De Morgan's theorem is correct, it means even after applying De Morgan's theorem, we should have true. Let's see how this will work. In line 36, we have the same thing here, but here we are applying De Morgan's theorem. So let's go back to the basics. The rule is like this. To use De Morgan's theorems in the logical operations and or and a pair of operands, we need to invert two operands, replace and for or for and. So let's replace and for or for and. In our case, we have or, so we represent or we convert this or to an and. We change this or to an and. So we have not A or B. Not A and B is equal to not A and B. Now, if not A is what? Here we have the same thing. Not in open and close parenthesis A and B. But what is A and B? So let's look for A and B. A is true. B is false. Okay? Now let's go to the presentation and see the value of true and false. And the value of true and false, if it is true, we change it to false. If it is false, we change it to true, because here we have not the value of this. So first we'll look for the value of this. Okay, let's go back to the presentation and look at conjunction table of truth. Here we have the conjunction table of truth. So if it is true and false, we have false. For true and false, we have false. Now our answer is false. Yeah, but we have not this. So if the answer of this is false, not false means we have true. Exactly. Not false is true. So let's run the program again and see. Not false is true. So here we have the same thing, true and true, meaning that De Morgan's theorem is very correct. And we have just proved that by applying De Morgan's theorem without changing the result. Okay, and that's it for this lesson. I hope you've learned something useful today, and I would like to thank you for your time and attention. Till we meet again on ITVDN.